First question. A beaker is filled in with water. Okay. A beaker filled with water is excited a meter per second square in x direction. The surface of water shall make an angle. Oh god, really? Which is this thing, right? Okay, whatever. So the effective rate just has a in this direction, g in that direction, and this will be like theta with x axis 90 minus theta. So basically tan theta equal to what? G upon a or something. Yeah. No. No, no. That's not tan theta. Wait. What is tan of 90 minus theta? That would be G upon A. So yeah, what we are talking about is like cot theta. Yeah, okay, so tan theta will just be A upon G, right? So tan inverse of A upon G, um, forward, backward. What does that even make sense? How does that even make sense? What do you mean by backward and forward? I mean, what? What is forward and backward? I'm just gonna say it's tan inverse of A upon G. I have no idea what this is. Okay, so tan inverse of A upon G or cot inverse of G upon A. At least that makes sense. Um, but what is forward or backward? I don't know. I don't know. Uh, but it is like negative, so I guess that's related to backward somehow. I have no idea what's going on, but just assume it's like backward. Okay, awesome. So it's backwards, and it's like tan inverse of A upon G. Yes. So this and that. So no, it's backwards, right? So A and C. Next question. Second. Second is the vessel shown in the figure has two sections. The lower part is a rectangular vessel with an area of cross section A. Okay, upper part is a conical vessel of height h with base area A and top area water. Okay, angle 30 degree with okay, that's given in the figure. The force F exerted by the liquid on the base of the vessel is. So this is a rectangular vessel, right? Okay, the upper part is a conical vessel. Okay, fine. Why is this rectangular though? I mean that would mean there is also some stuff from the walls itself, right? Okay. Neglecting atmospheric pressure, the force exerted by the liquid on the base of the vessel. So this is 2, what is this thing? 2h rho g times capital A plus small a upon 2. What? What is this pressure over here? We don't know that. Hmm. Oh, neglecting atmospheric. Okay, fine. And is this part like top area A? Right, I'm assuming this part has zero pressure because it's like open to atmosphere or something. I have no idea what's going on. But yeah, I guess this could be just open to atmosphere, which mean that okay, that's not it. Yeah, so atmosphere pressure is just zero. That just means like over here the pressure is just rho g h and whatever. Right. So just rho g. Oh, this is h. This is 2h. Fine. So like rho g 2h. Yes, but not this thing. Capital A plus small a upon 2. That doesn't make any sense. It just has to be capital A actually. Right? No. Okay, the pressure P at the base of the vessel is rho, okay, 2 rho GH and then capital A upon small a. I have no idea how that's working out. What is this? It should not make any sense. Yeah. The liquid of density rho fills both the sections up to a height of 2h. What do you mean by both the sections? I mean this and that. Okay. No, these are just wrong. The weight of the liquid W is greater than the force exerted by the liquid on the base. So, okay, the force is actually like, so on the base, that would be like the weight of the liquid plus some force because of these, because of this cone thing, right? Yeah. So actually it's weight of the liquid is actually and we want what? The correct option. So the liquid is greater than the force exerted by the liquid. No, that's so strong. The walls of the vessel exert a downward force F minus W on the liquid. Walls of the vessel exert a downward force on the liquid. This is getting interesting. So there is definitely this downward force because of this cone stuff, and then there's this upward force because of that. And I guess they don't match up, right? Yeah, that would be the only thing possible. So this is 0 over there. Okay. 180 this thing is 2 pi r dr, and then that times of h. So okay, actually rho g h, so like this times of rho g, and h would just be like capital H upon small upon capital R times yeah, like the whole thing actually. And small a is, we didn't actually, they didn't actually tell us the thing. That's not good. Initially we don't know what the thing is. So what's the capital H thing? We would never know in that case. Uh-oh. Base area capital A, okay, top area small a. This is getting weird, really weird actually. It does depend on what small a is, but all in all, we just know it's actually downward, right? Huh. How do I even do this? I have no idea how to start this. Okay, yeah, I mean, at the base we can actually figure out the force would be, but then this stuff. And what is F, by the way? Oh, the force F exerted by the liquid on the base of the vessel. That's definitely not this thing. I don't understand how this can be the thing, because it has to be pressure times, yeah, it has to be like pressure times area. So how is this going to work? No way, no way. It doesn't work. But yeah, like F is the force exerted by the liquid on the base of the vessel, right? So F is also the force exerted by the base area onto this liquid. And yeah, okay. Okay. It's F minus W on the liquid, that's the wall of the vessels. Sorry, walls of the vessel. Is this the wall or not? Oh, these are in fact walls. Very weird. Anyway, so that actually makes sense. So what that would mean is, why is this actually, this should have been cylindrical, right? But actually this is a rectangular vessel, huh? Lower part, fine. Anyway, this looks correct. So this is the, it's a downward force. That's F. Yeah, okay. So this plus W equal to F. Yes, that makes sense. So D would be correct. Second D. Didn't see anything else that would be correct. Next question. Third is the weight of an empty balloon on spring balance is W1. The weight becomes W2 when the balloon is filled with air. Let the weight of the air itself be W. Neglect the thickness of the balloon when it is filled with air. It's an empty balloon on spring balance. Okay. The weight becomes W2 when the balloon is filled with air. Let the weight of the air itself be W. Neglect the thickness of the balloon when it is filled with air. Also neglect the difference in the densities of the air inside and outside of the balloon. Thickness of the balloon when it is filled with air. Also neglect the difference in the densities of air inside and outside of the balloon. Then, so, okay, this is the thing, isn't it? It's kind of a weird thing. There's like buoyant force and force. Oh, I get what's happening. So here's the balloon. It's inflated. There's this air inside. There's yeah. So like for this whole system, what are the forces acting on? There's gravity because of this air, so W. But then there's also the buoyant force, which is also W. And then there's W1 because of the balloon itself. So yeah, that weight W2 is just equal to W1 in fact. So A is the answer. Next question. Fourth. What about W though? Well, okay, so W2 equal to, no, that's wrong. W2 is bigger than W1. No, it's equal to. W2 is less than W1 plus W. But yeah, because they are equal, so this plus W would definitely be bigger than that. So C is also correct. So third C is also correct. Next, a cubical block of wood and wait, delete all of this. Cubical block of wood of edge 10 centimeter and mass something floats on a tank of water with oil of relative density 0.6 to the depth 4 centimeter, or okay, above water. A tank of water. Wait, what? With oil of relative density, what? Oil? What are you talking about? Oh, okay, I think I get what's happening. Okay, when the block attains equilibrium with four of its sides edges vertical. Okay. Ah, right. So it's a block of wood of edge. Sorry, yeah, of edge 10 centimeter and mass this thing. This is relative density zero point 0.6 and depth 4 centimeter above the water, right? Okay, have very bad idea about this thing, but okay, just when it's an equilibrium, right? Yeah. Okay, this thing is 4 centimeter and whatever, and the block is of okay edge 10 centimeter and mass this thing. So like, what its density is? Do we even need a density? No, really, we don't. So the mass, which is like the weight or something, gravity, whatever. So like mg is equal to the fraction of the volume inside. Suppose it just is on the oil, right? So then that times the density of the oil, right? Yeah, let's see if that happens. If x is actually less than 1. Okay. So the mass is this thing, 92, okay, 0.92, right? And okay, this should be times g, but then that cancels it anyway. So 0.92 is equal to x times. So what's the volume of this thing? Just 10 power negative 1 power 3, right? It's 10 power negative 3. The times of density of the oil, which is like zero point 0.6 times 10 power 3, right? I guess that makes sense. So that just means zero point 0.6 times x. Yeah, it's equal to this thing. So x is just equal to this a 0.6, which is like 9.2.6, which is not less than 1. So yeah, this won't work. So the other thing would just be it's completely like okay, it's like this, right? Yeah. Then that would mean that m is equal to, so that's kind of weird. Um, there's this constant volume, so it's actually this base area times, let's just say this is the x that we are looking for. So the base area times this height like that is called h, right? So a h and then density of oil plus this point for solar of this thing, which is just ax times density of water, right? Okay, let's do it. So what the mass? Mass is just 0.92. Our area is how much? It is 10.82. Our h rho thing. So h is 4 centimeters, 4 times 10.82. That times of density of, let's do the thing, 4 times 10.82 times the density of what? Oil. Okay, which is zero point 0.6 times 10 power 3. So like it's just 10 and then 6 times 4 is 24. This is the thing. It's 24 right there. Plus x times, which is actually length, x times of rho w. So 10 power 3x actually. Which means 92 is equal to 24 plus 10 power 3x. So that means 4 like 7 and then 6 and 8, 68 is equal to, right, so x is just equal to 0.068 meters, that is, right? So it's that much, right? So this is a 1 centimeter, okay. So this is in meters, you want in centimeters, of course. It should be 6.8 centimeters. Okay, that's weird. I don't think it will be like this thing. Did I mess up somewhere? A is just that, and then you want h times rho naught. So it's 0.6 times 10 power 3, just 6 times 10 power 2, and that times of, yeah, this thing. So just 24 times. Yeah, that works out. Sure. Then x has to be this thing, in fact. It has to be. So combined like this and that, combined, it just becomes how much? This is in centimeters, this plus that is 10.8 centimeters. That's not gonna work. So it should be actually 10.8 centimeters. Oh, yeah, it's more than necessary, right? Which means just like actually go down. Wait, that doesn't make sense. How can this be correct? Uh, no, something's wrong. Something's wrong. That's 68, but how? How is that even correct? It's 6.8 meters, but then that's 4 centimeters. So it's in centimeters, right? Okay. And it doesn't make sense. It doesn't make any sense. Something going wrong. Something's going wrong over here. That goes inside like 92 is equal to 24 plus 10 power 3x. Sure. Density of water is just 10 power 3, of course. I mean, that's what we did all the time. What's going wrong? Just what is going wrong? I can't understand. What? It's like x times of rho w. Rho w is 10 power 3. The next or there. Okay. What's wrong? What's wrong? Well, this didn't work out. It needs even more volume immersed in water to actually get something done. So it will never be enough, in fact. Which means its density is just too much. It's gonna fall down. Right. It will actually be falling down. Yeah. Yeah. That is the thing. But it will actually fall down. So even if it's completely immersed in water, then okay, it could be that it's just interesting. Oh, okay. So this wasn't enough. Let's go in even more. So now what will happen is like it's actually gonna move like this. Okay, that's not good, but whatever. Okay, so let's just say this fraction is so like this will be x, and this is just the length of this guy, which is zero point 0.1 minus x, right? So then you just have the mass is equal to this volume, which is well, this is area, just 10.82. So you will have the same thing. 92 is equal to that was the thing, right? 92. Where did that go? Where did it go? 92. Yes, it's equal to the area is gone. It's just x times density. So x times right. Okay, you know what? Take the density of water out. Just 10 power 3. Then it's like 0.6 times x. So that. Oh no, it's like 1 times x actually. Just x, and this will be zero point 0.6 times this into. So like that's 0.06 minus zero point 0.6x. This will be of course, but they're just zero point 0.9. So 0.092 is equal to 0.4x plus 0.06, right? Which means 0.92 is equal to 4x plus 0.6. So wait, no, 0. Yeah, 0.6. That goes for this 0.32. Oh yes, like x is just equal to 0.08 meters, of course. So yeah, that's equal to 8 centimeters. So it's 8 centimeters underwater. Yes, this is 8 centimeters. So D is correct. For fourth, D is correct. So to centimeter of it will be about the common surface of oil and liquid. Yeah, C is correct as well. And what's this thing? About the free surface of oil, 5 centimeter underwater. No. So C and D. Next question. Fifth. Fifth is the spring balance A reads 2 kgs with a block M suspended from it. A balance B reads 5 kgs when a beaker with liquid is put on the pan of the balance. M suspended from it. Okay, it reads what? 2 kgs. Okay. Balance B reads 5 kg when a beaker with liquid is put on the pan of the balance. What? Balance B reads 5 kg when the beaker with liquid put on the pan of the balance. Oh, okay, just the liquid, right? Okay. Uh, no, okay, the spring, right. So when it's just suspended, it reads 2 kg. When it's like this, it reads, oh, I understood. Right. And when it's just the beaker, it reads 5 kgs. When the two balances are now arranged so that this happens. Okay, so what's the reading of the balance, right? Oh, of A and B both. There's a buoyant force involved in there and whatnot. Okay, densities or something that didn't actually tell something. So, mass and suspended for it is 2 kg, and then this reads 5 kg. When okay, okay. Nothing on density is actually given, so that's weird. Huh. Well, it's definitely down. This means it's actually going to, yeah, it's not floating, right? That's important. It's not floating, which means it's actually more dense than water, right? Okay, of course, A will read less. So balance A will read less than 2 kgs. Yeah, and B will read more, right? Because there's like that buoyant force you have to deal with as well. So it's more than 5 kgs. So fifth C. No, just read more than 5 kgs. That's that kind of interaction with it, right? Yeah. So A will read more than 2 kgs. No. That's even, okay, so B is correct. B will read more than 5 kg. And C is correct. So B and C. Next question. Sixth. Sixth is a tank is filled up to height h with a liquid and is placed on a platform at height h from the ground. To get maximum range xm, a small hole is punched at a distance y from the free surface of the liquid. Okay, then y is equal to y equal to small h, of course, and xm is equal to h. Sorry, 2h in fact. So xm equal to 2h. Yes, A is correct, and y is no, that's wrong. Okay, C is correct. So A and C. We have seen this 1,000 times now. Next, water coming out of horizontal tube at speed v strikes normally a vertical wall close to the mouth of the tube and falls down vertically after impact. What? Okay, okay. When the speed of water is increased to 2v, fine. Doubled. I mean, there's atmospheric pressure, but then just ignore that. So thrust exerted by the water. Okay, it's like half. Wait. It's m dot v, right? And that will be like what? Just rho a times v squared. But then the v squared thing is like 2gh or whatever. Oh, so just coming out. Ah, okay, understood. When the speed of water is increased to 2v, that just like is 4 times. So the thrust exerted by the water on the wall is 4 times. So B is correct. And what does it think? The energy lost per second by water strike. What? Energy lost per second by water strike of the wall. So 4 times. I mean, kind of it. It's like m dot, and then so the energy lost like because of that dm mass. So it had dm like half mv squared, and then this energy is lost per second or something like that, right? Yeah. So half m dots like half rho a v cubed, assuming rho and a are constant. Yeah, has to be the thing. So like it's 8 times now. So D is correct and B is correct. Seventh is P and D, right? Next question. Eighth. It is a cylindrical vessel is filled with liquid up to height h. A small hole is made in the vessel at distance y from the liquid surface is shown. Right, liquid emerging from the hole strike the ground at distance x. If y is increased from 0 to h, then x will decrease and then increase. Okay, so like of course it's two square of uh, y times of h plus y, right? So as y is increased, yes, this will actually like, right? I mean, we know just kind of like this thing, right? No, it's actually this. Yeah. So to become a maximum value at this is gonna increase when y is increased, right, from 0, right? X will first decrease. No, that's just wrong. If x, okay, x is maximum for y equal to h upon 2, I believe in that. Maximum value of x is h upon 2. Okay, interesting. Increase from 0 to h. X will decrease then increase. I don't think that's correct. Okay, then the x maximum for y equal to h upon 2. Yes, I believe in that. Maximum value of x is h upon 2. No, it's h itself, right? Because yeah, maximum value of x increases with the increase in density of, no, it's independent as you can see. Right. So B is the only correct thing. Okay, ninth. A steady flow of water passes through a horizontal tube from wide section X to the narrower section Y. Manometers are placed at P and Q at this section. Which of the following statements, okay, is most correct? Most correct? That's weird because it's a multiple choice question. So how am I supposed to do that? Huh. Water velocity at X is greater than that at Y. No, that's just wrong. It's just plain wrong. Yeah, because it is in fact bigger than Y. Continuity equation. Manometer at P shows lower pressure than at Q. Q shows lower pressure. So no, that's wrong because P shows higher pressure. Kinetic energy per meter cube of water at X is equal at X, okay, equal to kinetic energy per meter cube. What is this? Per meter cube at Y? No, it's not. I mean, like over here you have higher speed, right? So it's definitely more in this case. The manometer at P shows greater pressure at greater pressure than at Y. What? Manometer at P. Oh, okay, over here. Shows greater pressure than at Y. Yes, I believe in that. So D is correct. 9D. Next question or the next section or whatever. So exercise number 3. Comprehension type. Well, how many comprehensions do you have? Just have 2 comprehensions. Well, okay, that's such reasoning. That's weird. Anyway, Torricelli was the first to divide or whatever. Okay. Huh? Oh, so okay. Took a calibrated hard glass tube 1 meter in length. Oh, so the length is 1 meter for what? Calibrated hard glass tube and of uniform cross-section close at one end. He filled the whole tube with dry mercury, taking care that no air or water droplets remain inside the tube. Close the opposite ends of the tube tightly with thumb. Inverted the mercury tube into the mercury. What? Mercury trove. Or I think this area, whatever. Fine. Taking care that the ends of the ends of the what remains inside the mercury trove. Okay, of the tube, of course, but then whatever. An interesting thing was noticed: mercury in the tube fell down at first and then stopped at a particular position. Okay, the height was 76 centimeter above the free surface of mercury in the trough. What is this trough? Whatever. When the given tube was inclined or lowered in mercury, okay, trough, the vertical height of mercury level in the tube was always found constant. Torricelli explained this by saying that the mercury column is supported by the atmospheric pressure acting on the free surface of mercury in the trough. Hence, these hydrogen. Okay, I know that. Why do you give me all? There's literally nothing that is related to the question, right? Except that you have 1 meter length for this tube. Whatever. If a small hole is made at point P in the barometer tube, so at this point, okay, then mercury will come out instantly from the hole. I mean, this is P naught outside and this is a lower pressure, isn't it? Because this is 0 here. I mean, we assume it's 0, it's Torricelli's vacuum. Then, yeah, I mean, pressure P naught is over here and it's between these two, so it's supposed to be lower. Which means it won't come outside. It will, like, in fact, like, go inside. That doesn't make any sense. But something like that will happen. Okay, so maybe like bubbles will come inside. I don't know. Mercury will not come out of the hole. After some time, well, yeah, that looks correct. That does, wait, no, it won't come outside. It's just that this level will actually drop, right? Yeah, will not come out of the hole, none of the above. We will have like pressure P not introduced over here, right? Then it's like going down. Does it even come out? I have no idea. I don't think it will come out of the hole. So C must be the thing. So yeah, I think C is the thing. So it's like paragraph. So first C, it will not come out of the hole, I think. It is kind of complicated though. What if it does come out, but it's later on? Because there is a pressure difference, and then this is like higher, so air at least will try to go in inside because of the difference in pressure. What is supposed to be happening though? Like you will have kind of like a cavity inside of air. right? Yeah, that's weird. So what I'm thinking is like you have a cavity of air inside. So here you have mercury. What is this? Seriously, this is so weird. But now that the pressures are, yeah, so like this will of course go down actually. It's weird. It's really weird actually. And as it's going down, will the pressure ever become higher or something? I don't know. What can we assume? It's like Bernoulli's equation or something. Okay, maybe. We have like some flow speed over here and okay, think about it. Sure, you could do that. It's like some flow speed and then there's some flow speed over here and whatnot applies by the Bernoulli's equation. Like you have of course the highest flow speed. The pressure will be lower in that case, right? Oh, then no, it will actually not come out, it will just settle down, in fact. As you open this, so it will just not come out. It will actually settle out, settle down, and then nothing will happen. This is an unexpected result. It doesn't look natural to me though. But that's what Bernoulli's equation tells us at least. That as it's moving, its pressure is still lower than that, so it will never actually come out. I'm more interested in what happens to air, in fact. So should the air come inside because there's a like sudden difference in the pressure over here, so air will start to come inside. Okay, that's very weird. Problem is it's not steady state, so I have no idea how to model this. Okay, next question. Second is if an additional hole is also made at P dash at the top point of the tube, there's P and P dash. Okay, then so just like forget what's the question. Yeah, in that case it will in fact come up. So if both are made simultaneously, yes, mercury will come out of the tube. Wait, it's weird. It's just lower. Okay, it's like pushed down actually. Hmm. So first it will come out, then it will get lowered and won't come out. Right, so I think C is the thing. It will come out instantly. Third, if this experiment uses water instead of mercury, then length of water will be equal to 76 centimeter. What do you mean by that? No, that's just wrong. Length of water will be less than 76 centimeter. Length of water will be, oh come on, do I really have to do that? So it's like 1 atmosphere is 10 power 5 equal to rho gh. Rho is 10 power 3 times 10 power 4 times h, right? Wait, that was right or not? Rho, then g, then h. So like h equal to 10. So it would just be 10 meters. Oh, that's quite long actually. 10 meters, that's a lot. So it's like definitely more than 76 centimeter. More like it's, yeah, okay. That's very weird. That's definitely not supposed to be happening though. It will just not come out, right? The water will not come out. Even if you hold it up, even if you like make it go up. So you are holding like this water inside and still not coming out because guess what? This height is less than 10 meters. So you have, oh wow, this is very weird. So if it actually comes out, then you have like zero pressure over here, and that is making sense because how did this happen? So wait, is this for real? What you're saying is if I can actually fill, oh wow, but no, like how can this happen? So what you're saying is if I filled a container with water and then I closed it, then I remove the lid, the water will never come out. Huh? That feels unnatural, doesn't it? But that's what it's saying. So for that, so the length required so that it actually will come out is 10 meters, right? Or something like that. This is very weird. Oh, there's also surface tension. So okay, we are actually not including those effects. Those should be included. So to like form a droplet. Huh. Okay. Okay, that's very weird. Uh, wait, that outside pressure is actually higher, and then this pressure is actually maybe it will just lower the pressure inside. So then it's just forming a meniscus like this, and this is getting weird. I'll have to see if there's a demo for this thing or if it actually happens in the first place. What it's saying is that h would be 10 meters if we did this experiment, and of course our tube is just 1 meter, so weird. So length of water will be greater than 76 meters. I get that. C is correct. But this is a ridiculous height. So for everyday objects, this should basically give us that, yeah, your water won't come out. But that feels unnatural. I'll see what happens. Anyway, next, if the apparatus used for this experiment is kept in a chamber and all the air from the chamber is pulled out, then of course mercury will just come down. What's the, yeah, like level of mercury will become zero because yes, all the air is gone. So that has to happen. Inside there's vacuum, outside there's also vacuum. So right, C is the answer. Next question, fifth. In Dorsey's experiment, the length of the free space in tube is. What do you mean? Like this thing? I mean, that's 76 centimeters, so this should be just 100 minus that, right? Which is 24. 24 centimeters is the free space. Yeah. So B is the answer. Okay, assertion reasoning type. So assertion reasoning. First, when a body is inside a static liquid, it experiences what? It experiences up by Poisson's force because, man, their grammar is just so not good. I think it's an upward force. Wait, what is up by Poisson's force? Because what is this seriously? What is this statement? I get it, it's just the upward buoyant force, that's a statement, but look at it. Just look at how they posed it. Okay, pressure varies with depth in a static liquid. Yeah, that's right. So yeah, looks like a correct explanation for that. So yeah. Yes, it is in fact a correct explanation. So A is correct. I mean, the main reason is that it varies with depth. The other part, like doing the integral correctly, well, that's not important. Okay. Bernoulli's theorem is conservation of energy because mass flowing per second at every cross section that tube of flow corresponds to incompressible liquid remaining constant. What? Man, like the second statement. Okay, that's not statement two. This is statement one once again. Seriously, they put zero effort into making this, right? Yeah, but right. So the second statement is conservation of mass. That's not what Bernoulli's theorem is. So statement one is true. Yes, it's the conservation of energy, but then statement two is also true. It's not a correct explanation though. The cross-sectional tube of flow corresponding to incompressible liquid remains constant. Yeah, okay. Wait, at every cross-section of a tube, right? Not a tube with, like it opens into two tubes. That should not happen because then it's not correct. Okay, whatever. Two is correct, one is correct, not correct explanation though. B is the answer. B. And okay, so because this, the reason should be that viscous forces are ignored, and that's why you can apply conservation of energy. Okay, let's go to the next one. Third, wait, is that eighth for some reason? Oh, okay, so this is actually in continuation with that. Weird. Okay, weird. Sixth, this is seventh. Go to eighth now. When container containing a liquid accelerated horizontally, Poisson's force is not vertical. Okay, because pressure also varies horizontally when container is accelerated horizontally. Yeah, that's the thing. Sure. So this is actually a true thing. It is a correct explanation. So A is the answer. That should do it. And this contains 20 questions. I think we'll save it for a different video. Okay, then that's it. I guess we'll meet in the next video. Goodbye.